I'm excited about today's workshop of learning to do moles and stoichiometry and how to teach it well to our students. Because it's one of those skills that if we teach it really well, they're set up not just for the rest of our course, but for any chemistry course they have to walk into, whether AP Chem or going into college chemistry. If they can really have a good foundation with moles and stoic, then I really feel like they're set up to succeed. So with that, let me get started. Turn off my video. And so, all right. So those of you who are new this week, I grew up outside in Metro Atlanta in a town called Marietta, Georgia. It's up in the northwest corner of Metro Atlanta. Not quite a native Atlanta. I moved there when I was 3, but that's where I grew up. And so then I got my degree in chemical engineering from Georgia Tech. Because I went through school and I loved chemistry and I was good at math. And all my teachers were like, "Do engineering because you're good at math." I'm like, "Okay." But as I was getting through there, really probably my junior year and really into my senior year, I'm just kind of like, I really don't want to do this. This isn't what makes me happy. This is not, I'm good at it, but it's not like the thing that makes me really excited. And so I went back to get my education degree and I kind of got evidence firsthand if I made the right choice. Because the guy I was rooming with, he was an engineer working for Lockheed doing aerospace design. And he would literally skip his lunch break every day just to get home an hour earlier because he hated his job that much. And I did not want to do that to myself. And, and teaching's always been that place. There have been very few days in my teaching career where I was not excited to go to work. There were very few days that I dreaded going to work. If I did, it was probably because of like some meeting with a parent, some standardized testing I had to proctor, or something like that would make me dread going to work. But ever since I started teaching in 2001, I get excited about teaching. That's what I want to do. And so, that's where I want to pour in my life. And so that's been my life since 2001. And really, I think, one of the things I would really say about myself is teaching was always less about what I did, and it was more about who I was. I'm a teacher at heart. Like, I don't have to be in a classroom to start teaching. And so then throughout my teaching career, I've taught primarily smaller private schools. So I've had lots of preps. I've had as many as 6 preps in a year. I've had as few as 2. It's the fewest preps I've ever had. So I've always had multiple preps. I've always been teaching lots of things. I even had a stint as an administrator for 3 years, including a interim headmaster position. So interim running a school while teaching 4 classes a day. It was not fun. But that's part of my story, is so also being an administrator and part of my story. And so I left the classroom a year ago this time last year, I was still planning on going back. And then really just felt called to devote myself fully to this. And so that's been my life for the last year, is trying to come up with ways to serve you as chemistry teachers. All right, so first strategy for teaching moles and stoichiometry. And once again, if you've been through any of these other workshops, some of this is going to sound familiar because to me, the good fundamentals of teaching are going to be the good fundamentals of teaching. And also repetition is also just a good way to teach. So for me, you got to lay the foundation. I've never been good at doing stacked house of cards because my hands just aren't that stable. But with a house of cards, if you don't have a good foundation on the bottom, you're never going to be able to get up this high. You're never going to be able to build that up. And so you've got to build the foundation. And so the question is, when it comes to moles and stoichiometry, what's the foundation? Well, the foundation is conversions. So that's the first thing they have to know. They got to be able to do conversions. For me, I like to do this right before I do moles. So I don't do it when the book says do it. I move it later, and I do it right before I do moles and stoichiometry. I teach conversions. If you're someone who likes to teach conversions earlier on, like in chapter 1 or chapter 2, like most chemistry books have it, then that's fine. That's your choice. You can teach it there. Just know that to really have the best success in moles and stoichiometry, you're going to want to kind of reteach it here. You're going to want to go over it for a day or maybe 2 just to get them refreshed on how to do it. And I like to start with everyday units. I like to start with like feet and miles and things like that because I want them to be able to understand what they're converting and it not be so abstract. And then reactions, specifically balancing reactions. Balancing reactions is a prerequisite skill for doing stoichiometry. If you don't have a balanced reaction, then stoichiometry doesn't work. And we'll kind of get to how often I do that and ask them to balance it kind of later on. All right. Part of the foundation also comes back to, and once again, this is something I've been harping on all summer long, and if you listen to me anymore after this, you're going to hear this over and over and over again. Student-driven pacing. And what I mean by that is student understanding drives everything. If my kids don't get it, I don't go. I don't move on. And somebody asked a good question last week. Well, what do you do if you have like a third of your kids that still aren't getting it? Oh, that's where you start having conversations with them about coming in before school, after school, during lunch, during study hall, that kind of thing, doing extra work. When you're walking around checking on kids while they're doing work, they're the ones you need to hone in on and help get them up to speed. And so, but as a whole, and it's one of those things you just get used to, how to gauge when your kids are ready for you to move on. And it kind of becomes a feel thing. There is no hard and fast rule of like, when you get to 80% of your kids understand, then you can move on to the next topic. And for me, it's not just units, but it's also within subtopics. So, like with conversion, like, do they understand how to do a one-step conversion before I add a two-step conversion? And I'm not looking for mastery. I'm looking for, do they understand, can they basically do a one-step conversion? And if the answer is yes, then I feel comfortable moving on to a two-step conversion or a three-step conversion and adding those multiple steps. But I want to make sure they get it before we move on. Otherwise, your foundation's going to crumble. Because if your kids can't do conversions, and you start adding mole conversions in there, you're asking them to do something with it that they just don't have the skill set yet for. It'd be like trying to say somebody like, hey, play Stairway to Heaven, and it's your second day on the guitar. Not going to happen. You need some skills developed there. So, it just takes time. So that's student-driven pacing. All right. So I'm all about methods and visuals. And if you had a chance to see my workshop on teaching chemistry for weak math students, a lot of this is going to overlap because I really feel this is essential. So for conversions, like I said, I like to start with everyday conversions, meaning feet to inches, inches to centimeters, miles, liters and quarts, and things that they can kind of visually see. I'm trying to keep it fairly concrete here at the beginning and not so abstract, because the whole concept of a mole is kind of abstract. Like, you mean to tell me there's 6.02 times 10 to the 23rd things in this thing? I'm like, yes. That like in a palm full of water, there's about 18 milliliters of water, there's that many molecules of water in your hand. And they're like, uh-huh. It's a crazy number. It doesn't make much sense. And so I want to start with things that are more concrete for them initially. So let me run through my method. So like, how many miles are in a million feet? 1 times 10 to the 6 feet. All right. So for me, my method looks like this. And the reason why I break it into a method is for both my weak students and for my strong students, for weaker or stronger in math per se, it gives them a framework. It gives them something to hang their hat on. It gives them a structure to work on. So they're having to think enough. And so I'm trying to give them a structure to kind of help them shape those thoughts and also to lessen the overall load on their brain. Because that's kind of my job, is to smooth out the path enough for them to be able to learn it. Still challenging, still pushing, but really trying to give them a framework to work off of. And so this method, I teach it these steps, and then literally every time I talk about it, every time we do a problem on the board, I'm like, given over 1. And then next thing I'm like, all right, put your units in first. And this is the place where I differ from most books. Most books will say, oh, you got to look at your conversion factor, find the one that, and kids get the conversion factors flipped all the time. I mean, how often have you seen a student with this flipped, with feet on top and miles on bottom, or they got it. They say that 1 foot is 5,280 miles. No, they get the numbers flipped. They get the units flipped. So by taking the time to slow down, I make them do the units first. And what I find is that when I make them do this first, they don't tend to flip it. They may flip it a little bit just initially for the first day or two as we're learning how to do this, but it's just going to be for the first day or two. Then they get the hang of it, and if they make a mistake, it's because they didn't do the units first. So get the units in first, and so it's like whatever units up here has to go down here to cancel each other out. And the first time I teach this, I have to do something silly like 3 times 2 over 3. Right? Some silly fraction on the board. I'm like, hey guys, what's the answer? They're like, oh, it's 2. I'm like, why? Well, the 3's cancel out. I'm like, exactly. So if I have feet on top of a fraction and feet on bottom of a fraction, they cancel out. Okay, and so I can kind of tie it back into something they already know. That's critical. The more you can tie back to what kids already know and kind of their basic knowledge of math and fractions, help them make that connection. To you, it may be obvious, and you may think it should be obvious to them, but it's not. Kids aren't going to make that connection because they're in science class. And as far as they're concerned, math class is a completely separate part of the brain. And the two shouldn't play together in their minds. And so it's your job to, wait, that thing you learned in this other class called math? Let's bring it into here. And they're like, oh, I'm like, yeah, exactly. And so it's critical that we bring that in for them and bridge the gap for them. All right. Once they get the units in place, what I tell them is match the numbers from the conversion factors. I'm like, all right, feet's on bottom. Look at your conversion factor. What's the unit that goes with feet? Oh, 5,280. And then so that's with feet here, so it goes with feet here. The one is with miles here, so one goes with miles there. And so I have them do that. That's why it's important to get the units in the right place first. Because, this unit and the unit you're going to is going to determine where your units go. Then you just match the numbers, and it's simple. And I don't make my kids memorize these types of conversion factors because they're just not important to chemistry. I make them memorize metric conversion factors, and I make them memorize mole conversion factors, or at least how to use them, how to find molar mass and all that kind of stuff. I make them memorize Avogadro's number, that kind of thing. All right, so that helps them match the numbers in the right place. And then we solve. And once again, a lot of books will be like trying to teach this like they teach fractions. And they'll say, numerator times numerator, and then denominator times denominator, and then simplify the answer. Once again, most kids, and me, myself, it's like, I don't mind fractions, I'll do them. But if I can do life without them, I will. Because they are more annoying. And so I really try to teach this without all the fraction mess. And so what I teach them is, all right, if it's on top, you multiply it by it. If it's on bottom, you divide by it. Simple. Okay. Once again, if I can keep this simple, then it works. I'm not concerned about being mathematically, technically correct all the time. I'm worried about my kids being able to use the skill and understand why it works and how it works. And so we solve. If they're doing a longer problem, so for example, if I wanted them to do feet to kilometers, if I want to know, hey, how many kilometers are in 1,000,000 feet? I would then give them the conversion factor for miles to kilometers and then expect them to be able to work it out. Okay. Another thing that I find really helpful for students is to use multiple colors on the board. We live with a very, very visual generation. And so like here, I've got it colored for steps. So here's my first step is in this kind of light green color here. And then my second step is this light blue color. And then my third step is the orange. My final step is the black. So you could do it that way, or you could color it like this, where you're coloring the different units and showing how this unit matches this unit so they cancel out, and this unit matches this unit. Depending upon whatever facet of what you're doing your kids are struggling with, I love using different colors on the board. All right. A note on that, little side note. If you have a dry erase board, Black markers and red markers are really, really popular. However, they tend to smear all over the board and leave really dark residue that makes it hard to read your board, or you're stuck there cleaning your board all the time. Blue, green, and orange expo markers do not do this. I tend to do most of my notes in blue, and then I highlight with green and orange, sometimes purple, because they tend to not leave that residue on the board and be kind of take away from the clarity of what's on the board. Just a little side note, not related to multiple stoichiometry, but that's a little side note of something I've just learned from my teaching career. Blue marker, like by the end of the year, my board will have a slight blue haze to it, but like I literally, from the first day of school until the last day of school, I don't clean my board usually until the last day of school. I don't have to break out the expo cleaner and do all this hard work multiple times during the year because I use blue and green as my primary colors. And then the orange also erases really well too. So just a little side note there. But I'm all about using colors to show kids steps and to clarify things, just helping them see things. Because when everything is in the same color, they can get confused as to what's what. All right, for mole conversions. If you have given your students a firm foundation with conversions, if you have made sure that they can do conversions, and you could give them a conversion question saying to convert whatchamacallits to widgets to doohickeys, and giving them conversion factors and they could do it, then you know they can do this. And so if they're really firmly grounded in conversions, then moles is simple. All you're doing is adding new conversion factors. Okay? And I love using the mole road. Mine, I've tweaked it this year. I've even tweaked it from earlier this summer for the math conversation. I've changed this from concentration to volume of solution. But all of these things are related to moles. And these are all things we use. Well, really, we don't use this one much, other than simply explaining moles to begin with. So, I use Avogadro's number to start with, but I really don't put a whole lot of emphasis on it because it's not one that I use. We don't worry about particles when we're doing calculations. We want to know, hey, I've got 50 milliliters of solution. How do I convert it? We've got, 100 grams of this. How do I convert it? I've got 3 liters of this gas. How do I convert it? Those are things that we measure. All right. And so I give them these conversion factors. Once again, these are things I make them memorize. Because for me, memorization in chemistry, at least for me in my class, I want them to memorize things that are going to save them time in class. So for example, element names and their symbols. I make them memorize the most common elements. I have a list of about 50, I think, that I make them memorize because it saves time. When they're having to look up on a periodic table the name of an element, it's wasting time. I make them learn their polyatomic ions. I don't give them a sheet with those things on it. Even my kids who struggled, who weren't my strong kids, I've had some like low-level classes. I've made them memorize polyatomic ions because it saves time later. It allows me to focus my energy on teaching mole conversions and not having to factor in the time like, all right, they're going to have to go back and look at this formula and do this thing with this name. They're going to have to do this thing over here. I want them to have that stuff memorized. Same thing here. I don't want them having to look this up on a sheet. I want them to know it. And I want them to do it. I want them to know how to calculate molar mass, how to count the atoms in it and figure out the mass from the periodic table, that kind of thing. You can kind of, with molar mass, you can kind of do decimals how you want. My general rule for molar mass is if it has a 0 or a 9 after the decimal, round it to the whole number. If it's not a 0 or 9, you got to use that first decimal place. That's kind of my general rule for that, reading the periodic table. All right. So let's run through an example. What's the mass of 3 moles of copper 2 chloride? So given over 1, and get your units in the right place. Okay, this is kind of how I would want them to get this. They wouldn't have to do this part yet, but I'd want them to write this and then have the units in place. And at this point in time, I'm harping on my kids early on, even in the mole unit, I'm saying, okay, do not just put moles. It's got to be moles of copper 2 chloride, CuCl2. And it's got to be grams of this, because I'm trying to set the stage for where we're going in stoichiometry. Because in stoichiometry, we're going to have moles of two different things. And so I'm trying to get them in the habit early on of don't just write moles of whatever you're talking about. What type of moles are they? Like we have inches, but we don't have different types of inches. And I guess you could have like inches in width and inches of length, but most units we don't worry about that, but we do need to worry about it here. And so they've got to add, that's part of the unit. If that's missing, it's wrong. I do harp on that. I tend to be pretty flexible on a lot of things, but with conversions, tend to be really nitpicky. All right, then you put in your conversion factor. 1 mole is the molar mass. Get this from the periodic table. Then do your math. It's 3 times 134.5 gives you 403.5. Or 404 if you want to use 3 significant figures. If you want to be exact on sig figs, it'd be 404. All right. So that's an example. And so they're seeing, hey, we're at moles, we're going here, so we use the molar mass. I like using the mole road initially early on because it makes them see how to do multi-step problems like this. So I'm asking them for the mass of something, and I give them the volume of solution. I say, hey, it's 0.150 liters or 150 milliliters. And so I give them this volume, and I'm like, all right, so how do you get the mass? You go volume to moles to mass. They see the steps. Once again, this is most of the kids in this generation tend to be visual. So what I do is on my homework, not only do they have to do conversions like this, but they have to draw this out. On a quiz, they're going to have to draw this out. On their test, they're going to have to draw this out. But I want to reinforce the visual to help them see it. All right, so like I said, I like to have them figure it out that we're going to go liters to moles to grams. Kind of write it out like that. All right, so once again, we get the units in the right place. Given over 1. And we're going liters, so liters goes away, and we're going to moles, so moles is going to go on top. Then we're going moles to grams, and then grams is my answer. Match in your conversion factors. Moles and liters is going to be the molarity, which is this guy. So 3 moles per 1 liter. And so that conversion factor goes there. This is the molar mass again, and then we get an answer. 60.5 grams of copper 2 chloride. And so that's doing mole conversions. Once again, if they get where the units go and they understand conversions, then this step is easy for them. They get that. This is what we did in conversions. They know what they need to do here. So all I'm teaching them to do in the mole unit is, hey, these are what the conversion factors look like. If the volume of solution, use this one, 3 moles per liter. That's what that means. 3 molar means 3 moles per liter. That's what that unit means. And then here's the molar mass. And for them, it becomes relatively easy. They're just learning how to do that. Also with mole conversions, that's where you do percent composition. And then determining empirical formulas. I meant to do a slide on that. I think it's an important skill because it just practices the mole conversions. And so it's just a good thing for them to be exposed to there as well. All right, stoichiometry. Builds on conversions, balancing reactions, and moles. If they are comfortable with all 3 of those, this is not complicated. This is why when I talk about student-driven pacing, this is the payoff. Because if they're weak here, if they're weak with conversions before you go into moles, then 90% chance or higher, they're still going to be weak with moles. And if they're weak with moles conversions going into stoichiometry, you're asking for a headache. It's going to be like pulling teeth. It's going to be like beating your head against the wall, and it's just not worth it. Whatever time you gained by going fast through these and not making sure they got it, you're going to lose now because they're not going to get stoichiometry. It's going to be like pulling teeth. It's not fun. However, if you take an extra day or 2 here and an extra day or 2 here and just make sure they get it and make sure they are solid, that they can do conversions and mole conversions in their sleep, they can balance reactions with ease, then stoichiometry is just really not that bad. Because once again, all you're doing is teaching them an extra step. You're teaching them the mole to mole step and I teach it first before adding the mole conversions on each side. Okay, so for example, use the balance reaction below to determine how many moles of oxygen are needed to react with 4.5 moles of C3H8 propane. Okay, so once again, I teach them, hey, take your given over 1, get your units in the right place. Note I'm emphasizing this. Hey, we're going from moles of one thing to moles of something else. So make sure you label which mole is which. Okay, and then they're like, well, where's the conversion factor? I'm like, well, in this reaction, how do I know how are oxygen and propane related to each other? They're like, well, one of these takes 5 of these and gives me 3 of these and 4 of these. I'm like, exactly. So 1 of these equals 5 of these. That's a conversion factor. So I teach them that's where that comes from. So 1's in front of C3H8, so that's the one that goes right there. That's 1 mole of C3H8. 5's the number in front of oxygen, 5 goes there. Okay, so just once again, I'm using the exact same principles, and I'm even saying it the exact same way that I've been saying it the whole time. Because I mentioned this last week in last week's workshop, consistency. If I'm consistently teaching the way I do stoichiometry is the way I did mole conversions, and mole conversion was the way that I did regular conversions, that consistency is going to make them more comfortable. It's going to register with them of like, oh yeah, okay, that's what we do. And they're going to register with that, and it's going to make things work a whole lot smoother. Okay, so I'll do a couple of these, and this usually, once again, if they're really comfortable with conversions, I can cover this in the first half of a period or less. Then I can add mole conversions on each end. So this is what I call the stoich road. You have the mole road. I call this the stoich road. And it works the same way. That, hey, we're going to go from moles of A to moles of B. We're always going to start on the left, and we're always going to go to the right. And then I start adding these mole conversions. And sometimes I add them, sometimes I don't. And we use this visual to kind of help us out. So I like to have them identify, where did they start on the left? Did I give you grams or liters, or did I give you moles? Where are you starting? And then what am I asking you to convert to? Grams or liters or moles? And so, for example, here's a question. How many grams of aluminum are needed to react with 4.5 moles of copper 2 chloride? You can tell I like copper 2 chloride. So we're starting with moles of copper 2 chloride, and I'm asking for not moles of aluminum, but grams of aluminum. So they should now see that this is a 1-2-step problem. So let's look at it worked out here. So they know that they need to go moles of A to moles of B to grams of B. So here's what that looks like. So changing A and B into what they're actually doing. So they're going moles of copper 2 chloride to moles of aluminum to grams of aluminum. That's what they need to do. So I give them the balance equation. Now, with stoichiometry, I mix it up. Sometimes I ask them to balance the equation, and I make it explicit. I'll say something like, use the following unbalance, and I'll like bold un and underline it so they can't miss the fact that they can miss it, but hopefully they won't miss it, that it's unbalanced. But I probably only do that about 10% of the time, maybe a little bit more. It kind of depends. Because a lot of times my emphasis is on the stoichiometry, not on the balancing, but I want to bring the balancing back in and kind of keep that fresh. And so I do bring it in, but I don't make them do it all the time, because I don't want them spending all their time balancing reactions on their stoichiometry homework. I want them doing stoichiometry on the stoichiometry homework. And so I limit how often I bring in the unbalanced reactions and make them do it. All right, so once again, given over 1. This unit goes on bottom, this one goes on top, and then this one goes on bottom, and this one goes on top. And you get your final answer. Once again, if they can get the units in the right place, the chances of them getting the numbers in the right place is dramatically higher. Mole to mole step is the same that we just did. Use the numbers from the reaction. So a 2 goes here. That's with aluminum here. 3 is with copper 2 chloride, so 3 goes there. And then this is molar mass. 1 mole is, whatever the mass, 27 grams. All right. If it's on top, you multiply by it. If it's on bottom, you divide by it. Usually 81 grams of aluminum with 2 sig figs. And so once again, I know I've already said this, but I'm just saying, if they can do conversions and if they can do mole conversions, this isn't that difficult. I can usually cover stoichiometry, honestly, including going over the homework, I really feel that most of my kids get stoichiometry in 2 days or less. It really is that fast because I've laid the foundation. That my kids usually do really, really well on this test because they already get it. Now, add to that advanced stoichiometry. Now, this is another thing. So, to me, this is percent yield and limiting reactant. And this is not just doing stoichiometry. This is taking stoichiometry and having to interpret the answer. And so, this is one of those things where I bring in a lot of illustrations. So, like to me, percent yield. I explain this using the idea of a cookie recipe. That hey, your recipe says you can cook 36 cookies, you only made 28. What percent yield did you have? Or what percentage of the cookies were you able to make? And they can figure it out. It's 28 over 36 times 100. And then I take that example and I'm like, all right, we would call the 28 cookies the actual yield. We'll call the 36 cookies that you were supposed to make, we'll call that the theoretical yield, how much you were supposed to be able to make. And then the your percent yield. And so I've given them something, once again, concrete that they can understand, and I've applied it to chemistry. Same thing with limiting reactant. The way I do limiting reactant, the illustration that I give there is grilled cheese sandwiches. Hey, if you got 2 pieces of bread, so I give them basically an equation, like 2 pieces of bread plus 1 piece of cheese, and you do have to be explicit. Because, there are people, I like 2 pieces of cheese on my grilled cheese sandwiches too, but so you got to specify that it's 1 piece of 1 piece of cheese. Otherwise, you get controversy in your classroom, and it's not worth wasting the 10 minutes of conversation that's going to take. So you got to be explicit. 2 pieces of bread, 1 piece of cheese makes a grilled cheese sandwich. And so I tell them, all right, you've got 10 pieces of cheese and 7 pieces of bread. How many sandwiches can you make? And intuitively, they can figure it out. And then I write the equation on the board. 2 bread plus 1 cheese yields, a grilled cheese sandwich. And then I'm like, so why did you only make 3 sandwiches? Well, because we ran out of bread. I'm like, bingo. We call that your limiting reactant because it limited how much you could make. And then we had cheese left over, right? Yeah. Right. We call that your excess reactant because you have excess. You have stuff left over. And they're like, okay. I'm like, all right, now let's look at it with stoichiometry and let's look at a reaction. And so once again, start with concrete, then take it abstract. Big thing for this, for both of these, is any calculations you do, any numbers that you're comparing have to be in the same unit. So percent yield, your actual and your theoretical yield have to be the same unit. You got to be comparing apples to apples. If they're not the same unit, then you can't figure out the percent. Same thing with limiting reactant. If you don't convert them both to the same unit, then you can't compare them to each other to see which one made the least and which one made more. And so that's a big thing I harp on. They have to be the same unit. All right, so with the percent yield question, what I like to do is I like to label the parts. I can't remember if I brought in an example here. Yeah, I did. All right. So if you start with 4.5 grams of calcium carbonate, then what is the percent yield if you recover 2.1 grams of calcium oxide? Give them the reaction. It's already balanced. What I want them to do is I want them to identify anything that's in the equation. So we're trying to find percent. This is my actual. So I want them to underline it and write actual. And then I'm going to have to use this to find the theoretical. And then they're like maybe draw an arrow and say, get theoretical, something like that. Okay? And so that would kind of be the general idea there. And I think my PowerPoint just crashed. Hold on one second. Gotta love technology sometimes. All right, so PowerPoint just crashed. Hold on one second. And I can pull that back up, hopefully. All right, share it again. All right. And then limiting reactants. The way I do limiting reactants is I seek to, there are a lot of different methods I've seen where you convert from one reactant to the other reactant and you got to compare the numbers. It works. I just find it intuitively difficult. I think it's easier to ask the kids to convert to products. So I ask them to convert to moles of one of the products. Because I think, if I have a reaction that says, oh, it made this much carbon dioxide and the other reactant made another, this doesn't work, this is a decomposition reaction, but just saying, if we were doing it and we could compare amounts that were actually made, that makes more intuitive sense. Like they could compare the amount of grilled cheese sandwiches that were made that made intuitive sense to them. And so I want to keep it the same way. I want to compare things in such a way that are intuitive. And so I convert to moles of the simplest product. So I just pick one of the products and I convert to it. And I'm only converting to moles because why do an extra step if I don't have to? Why convert to grams if I don't need to? I just need to convert to moles and then I can compare the numbers and see which one made the least. The one that makes the least is the limiting reactant. Now, the exception to that rule is only convert to grams or liters if you're asked how much you actually make. If the question says, all right, which of these is the limiting reactant and how much do you actually make? How many grams of carbon dioxide do you actually produce? Then, when you do these calculations, convert to that unit. That's what you need to find out anyway. So you might as well convert there to begin with. And just trying to do it that way. And so I try to, once again, start with concrete. An illustration like, how many cookies do you got to get out of a cookie recipe for percent yield? How many grilled cheese sandwiches can you make for limiting reactants? Or whatever works for you. Those are good examples for me. And so I start with those concrete things, and then I build the chemistry off of those illustrations. And then, once again, I'm wanting to slow them down and make them identify parts that slows them down, gives them structure to work off of. It's good for structure, and method is good for weak kids because it just helps them not use so much brain space. It's good for your stronger kids because it slows them down. So they're not going so fast. Okay. All right, grading moles and stoichiometry. So for me, grading, I grade step by step. Because for me, given over ones, that's step one. Units in the right place is step two. And then numbers in the right place is step three. And then solving is step four with the correct unit. And so that's how I grade these. This is a conversion question, but I grade moles and I grade stoichiometry exactly the same. Now, by the time we get to stoichiometry, it may be that all of this becomes just 2 points instead of 4. But I kind of, depends what mood I'm in and how nitpicky I want to be with points. But that's how I do it. I just break it down by points. And because I'm trying to grade the method. I'm like when I first start teaching mole conversions, or when I start teaching conversions, when we're doing things like this, meters to centimeters to inches, we're doing the miles to feet or whatever. I'll always have that bright kid who wants to be like, hey, I can just do this with my calculator, and in my head, I'm like, do the work, show the method. Why? Trust me. Because at this point in time, when I'm teaching conversions, it's not about the right answer. It really isn't. That's part of the grade, but look at it. There's 1, 2, 3, 4, 5, 6, 7 points here. The right answer is only worth 2 of them. So if I have one of my smart kids, and I'll tell them, and I'll show this on the board, if all right, if you want to just give me the right answer and not show me any of this work, you get 2 out of 7 points. That's a 28. If you want to go that route, feel free. And that usually is enough to get them to be like, all right, I'll show my work. Exactly. All right. Because I'm teaching the method. Because I want them, because once again, I want them being really, 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 really comfortable with conversions. And then when I go into moles, my work's already done for me. And we can go through moles pretty quick. We can go through stoic pretty quick, and they're going to get it because they have a good foundation in conversions first. Okay. All right. So And then I haven't said this before, but the way I do this then is, so at that point, questions were 7 points. And let's say it's a quiz and they had 5 of those. That'd be 35 points total. And so their percent would be, let's say they got 33 out of 35 points, times 100 would give me their grade. And that way I'm not trying to make things add up to 100 points. I'm not trying to figure out, it's just like, it's however many points is on there and your percentage of those points, that's the grade. Once again, I'm trying to keep it simple for me. It takes a little training. Kids aren't used to it, how that works, but that's how I do it. I don't do a points-based grade book. I do a percent-based grade book. Like, you made a 73 or you made a 96. But I get those percents by using kind of a points-based system. All right, and so that's how I do that. All right, so the road forward, we got the rest of the summer workshop series. So we're here right now. So next week I'm looking at classroom management, and I'm going to look at it. If you've been around, if you've seen my workshops, I'm not going to look at it kind of how everybody else tells you about classroom management. I'm going to look at it a little bit differently. And then I'm going to go into student engagement in August. And all of these August workshops are going to be on Saturdays instead of Mondays. Because I know some of y'all will be going back probably right around here. So some of you who, were out before Memorial Day, you'll be going back, right there first, second week of August. Some of you have until later before you go back. But I know some of you, that's the case. And so, and then this one on the 10th, I've mentioned it before. This is meant to be for people who are primarily teaching in private Christian schools. One of the challenges that we face in that environment is how to teach really solid chemistry content while still adhering to the faith model of the school. And how do we blend those two together? And that is a struggle sometimes. It's a struggle for us as teachers. It can be a struggle for our students. And I want to kind of help bridge that gap. All right. And then working with teens is the 17th. And then this was my first one, but I'm going to redo it and probably add a little bit to it in terms of planning and pacing there on the 24th. All right. So when it comes down to it, my goal for teaching high school chem is to be here for you. We're coming down to crunch time. I mean, like I said, some of y'all start school in a couple of weeks. And so I want to be a resource for you because you can do what I did my first couple of years teaching. You can go it on your own. And it's hard and it saps a lot. If I hadn't been single at the time, I don't know what it would have done to my marriage. I don't know what it would have done to my family. And I don't want you to have to sacrifice your life outside of school to be a good chemistry teacher. And so that's why I'm providing these resources. The crash course, if you're really trying to struggle with growing and understanding the content of chemistry. And then the academy is more of my monthly membership of just having a community of like-minded people, but also giving you all the resources you need, all the handouts, all your assessments, all your labs you need to do a full year of teaching is there. And plus keys to the homeworks and the quizzes and the assessment. All that's there, and I do that to save you time. Because I want you to be a quality chemistry teacher, but have a life outside of school. And that's what I want for you. And in the same way, I want to continue to be a resource for you, and that's what I am for that academy. It's like, so usually it's going to be Sunday afternoons. I'm going to do my office hours for that group. And it's a time to not only just bring your chemistry questions, but if you're dealing with an administrator and you're just frustrated, I've been one. I understand how administrators think. Maybe I can help you talk through that. Or you're just really having a hard time with one particular kid, or you're having a hard time with a particular parent or a colleague. Whatever your struggle is related to teaching in general, plus teaching in chemistry in specific, I want to be a resource to you. But I want the whole group of the academy, the whole family there to be a family who supports one another and encourages one another. And so it's a place where we can bring the issues that we're dealing with. So I want to be that resource. I want to be that mentor teacher for you that when you need something, I'm there to help you. Because with the academy, like if you're doing that and you're working through it and you realize, hey, I need a handout on this, and it's not there, ask me. And I'll work on creating it. Because I left the classroom, which I love, to come and teach you, which I love, to be a resource to you to help you be a better teacher. That's the whole point of what I'm doing this. Um, and I really feel that, if you partner with me, if you invest in yourself by joining one of these, I'll be there to support you. And we have a community there to support you, and that you don't have to go it alone. And so that's what I'm looking for there. Um, so that's our workshop for today. And so, like, if you have any questions, I'll be on.